The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Before we begin, can I see by a show of hands if you can hear me and you can see my slides? There is attendees pane. If you can click on that hand icon to indicate that you can hear me. Brian, thank you. Emily, thank you. Thank you very much. Looks like we're all to go. Hello again. On behalf of Web-based Solutions, I would like to welcome you to our today's webinar, Apply Data Science Using Python. My name is Mikhail. I will be your instructor for today. Web-based Solutions has been providing a broad spectrum of regular customized training classes in programming, system administration, architecture, and now we also added data science to our portfolio of training materials that we offer. So that was the necessary plug. The overview of the talk. We will quickly review some of the Python data science libraries. Those are the actual very highly optimized algorithms and techniques to achieve the goals in data science. We will also just quickly review some of the samples of Python code dealing with a variety of problem domains in data science. The way I would like to structure this talk is to get your questions as we go. There is a questions pane that you can use to put in your questions. I won't be able to monitor the chat and the questions window. Unfortunately, that would be a split of personality for me. I cannot do it very well. So my focus would be on the screen with my right eye, and my left eye would be going to the questions. So feel free. I won't be unmuting you because we've got about 70 attendees and more people are coming, 71 and counting. What happens is that it'll be much too unmanageable environment. So as I said, put your questions in the questions pane and I'll try to answer the question. I'll be just one-man show. There'll be no kind of additional resources on this call, so I'll try to do my best. Definitely, I won't be able to answer any questions that you might throw at me. I guess the first best option would be Google. And then this is just an enormous field, which is very, in good faith, attracts lots of people from different backgrounds, whether they're statisticians, people who have a PhD and they're professors at some schools, and people just love kind of doing this stuff. So let's take a look at what Python can give us. First, we need to define what data science, machine learning, or artificial intelligence are. So lots of those things are used interchangeably with some, I guess, small caveats. And the common kind of a consensus is that data science kind of a bigger thing, which includes machine learning. And machine learning is just a subset. It's a subfield of data science, and which focuses on machine learning algorithms in the field of making predictions or taking actions on new data. So you learn, you train your machine learns from your training data, and then you probably validate, test your model, and then you expose it for making predictions. So that predictive capability or predictive analytics, when you hear about this, it's machine learning. And data science, it's a broader field. Probably you would be better off to put on your resume a title saying I'm data scientist rather than I'm machine learning engineer. It would be very kind of a specialized, limiting to a certain degree. But data science requires you to be more versed in statistics, maybe advanced data analysis. Machine learning about kind of engineering. You've got probably, I don't know, like Google TensorFlow, and you'll be kind of applying those neurons and a variety of kind of hidden layers trying to build that system that would do the prediction, right? And artificial intelligence, it's definitely a more advanced kind of a field where you, I would say, trying to substitute some very complex human activities, where you have some expert systems, maybe some very advanced computer vision type of setups, and you will be definitely in a better position to use deep learning and neural networks. Okay, so that's generally what I want to say first. Second thing is where you are. And again, as I said, put your questions if you have any comments, I guess, or questions. Okay. Where we are, just quickly, let me review this Venn diagram. So data science is at the kind of it's a focal point. It's at the core of all those activities. And machine learning is part of, it's not an exact kind of a representation of that problem domain, but it just gives you some sense of kind of a labeling where you are. Many people come from that substantive expertise. So you are probably a business analyst working in a department. It might be insurance, actuarial statistics, maybe in other fields in a bank, and you would like to probably move towards data science. So what would be involved? That's what people are asking. You would definitely, as a business analyst, you probably have some exposure to math statistics, but what's important to become sort of a well-versed, well-rounded specialist in data science, you need to have those hacking skills. It's not a very nice way to call this expertise as hacking. It's more of having background in programming where you are proficient with maybe Python, maybe R, maybe some other, maybe Excel, Visual Basic for applications, VBA programming. Hacking, it's more about kind of a mad type of scientist type of frame of mind where you want to experiment with data. There is nothing really cast in stone. There is no kind of rigid rules. You have to treat your data as some sort of evidence that you would like to use in your data science experiments. You would apply algorithms. Algorithms don't work nice. It might be because of the not properly fine-tuned algorithm or the wrong algorithm altogether, or maybe you have problem with your input data, how you extracted feature, how you engineered those features. So lots of things is involved. Okay, so essentially, to be a data scientist, you would first, I would say, math and statistics, programming, and then, if possible, you need to either have people on your team in your data science lab, or be yourself a little bit more knowledgeable of what problem domain you are in, what type of problems you are solving, because garbage in, garbage out, no matter how kind of a powerful systems you have at your disposal. Okay, moving on. I guess that's by way of introduction. I have to do that. I guess data science, machine learning, essentially consists of a number of activities, and there is a very nice diagram, I guess, which tries to depict all those things. We acquire data from some sort of input streams. It might be your partners, it might be your log files, it might be your sensors from the Internet of Things type of cloud. We get the data, and at this point in time, we essentially own the data. We onboard data, and now we can start applying. Data essentially has arrived in our data center or our data mart. Okay, so we've got operational data, which is probably log files, protocol buffers, and Avro. It might be Hadoop file system. External data from your partners, and you need to clean data. Essentially, you need to remove any outliers. It's a very important step Okay, don't throw away the baby with the bathwater. At this point, you can start doing kind of a reporting right away. So that's where probably you would have your existing data sensor capabilities for processing data. Maybe you have something from kind of big vendors. You will be building all up cubes, and you can start doing that analysis, pivot tables and such. But data science really starts after that. So downstream, you need to start thinking about what feature you would like to retain, which feature you would like to throw out, because it doesn't carry really any information. And maybe you would create synthetic features, feature crosses, multiplication of features, creating something which would be more representative. Very important. And Python, by the way, supports all those things. You can acquire documents over the internet through the RESTful services, RESTful endpoints, data from static files. But cleaning, removing outliers, data sampling, you don't need probably like terabytes worth of data to get some sense of correlation between some columns, because correlation might really skew up your results. You will probably need to drop some of the, to reduce that multi-collinearity, you need to drop some of the columns and clean up your data, end up having fewer features, and your model will be simpler, and for that matter, it would produce less errors. Okay, modeling data. At this point, you kind of start thinking about what should I apply? Is it labeled data, unlabeled? Would it be clusterization or clustering exercise, classification, maybe regression, maybe something else. Data partitioning is important to break your data into test data and training data. Training data is used for training your model so that the model is aware of the labels if we do classification, or the system would start coming up with those centroids in clustering, and testing data so that data would be used to validate if your data is your model is really capable of doing predictions. And then when you have this thing, you start building iterative approach using a particular candidate model, probably fine-tuning, adding some hyperparameters, just adjusting maybe lambdas, whatever kind of a C parameter, and all that stuff would need to work towards a single goal. You need to validate the model, and if we have that subject matter expert shown here, this guy is probably the gatekeeper. And if everything's fine, we are satisfied, and you probably fed your model some additional unseen before, like future real data, then you would expose it and build that accepted model, right? You can build something which you can use in production, which can start servicing the real data. Okay, and by the way, Python supports all that pipeline, right? That flow is supported, so that's critical. It's not kind of limited to kind of a model building, model validation. Like the whole chain of events is supported. So Python in itself, it's a good language really for learning programming and maybe doing some nice kind of homegrown projects. But when people have started, like data scientists maybe from academia, maybe some people in the field, they kind of got attracted to Python through that kind of a simplicity. You read the language as if it's written in plain English. And Python community came up with some of the systems which really enhanced Python capabilities. Like at least is that dynamic array is good, but it's kind of a little bit bloated. It has lots of functionality, and it's not very fast. NumPy was the first reaction to address that gap. SciPy was the umbrella project which included NumPy. Pandas borrowed lots of ideas from R. R was a major influencer driving some of the decisions made by Python groups. Scikit-learn is a package which actually deals with all of those things that we are going to talk about in this presentation. And it's machine learning package which depends on pandas, scipy, NumPy, and matplotlib. We just mentioned it here. It's just the graphics. It's building graphs, plots, histograms, and everything. It's most obvious, and we are not going to spend time on that. Okay, NumPy has been around for quite a long time, and it's open source software, and essentially it has that a fundamental concept called n-dimensional array. It's highly optimized. It uses that C bridge. Everything is allocated using malloc at the C level, and things are done very fast. Essentially, Python just delegates the processing of linear algebra, managing substringing, reshaping your data from a string, a kind of a one-dimensional array, a kind of string of elements into two-dimensional or multi-dimensional structure. So some of the operators, I don't want kind of to tell anything that you already know. So I guess you can just turn from the screen for a second, and but let me just quickly review those things for the benefit of those people who don't really familiar with those things. I'm not a very good salesperson, but I guess I'm just trying to highlight some of the points that you as a programmer or maybe business analyst would see being kind of important. So what we do here, NP, it's a way when we import NumPy, it's usually when you do NumPy, you do it aliasing. You can import everything from NumPy, but it's not a good idea because you just create a global set of functions which can start clobbering each other. It's a mess. Use that namespace. So NP is an alias to NumPy, and array is a way to pass on that list that you create, that's Python list, into the actual structures which are very compact, memory efficient, concise, small footprint, and written in C. Lots of useful, I guess, constants. We do pi, and NP cosine essentially, this whole statement is an indication that Python, for efficiency, supports vectorization. That's an example where you essentially apply a function. It's kind of, if you are familiar with MapReduce, that's a map. Essentially, you apply that function course across all the elements. R does this as well. So that permeates the whole kind of philosophy of pandas and NumPy. Okay, and we've got output, which essentially is the results of pi is 3.14 and with some change. Filtering, again, it's probably can be viewed as a functional programming kind of a paradigm, not showing even lambda here. You just get this array and you apply a predicate. So that predicate would retain all the elements which are even. Again, just give you a sense of what you can achieve with just minimum number of code. And reshaping, it's just a way to present your data, which is kind of a linear shape, just one-dimensional array, single row. You reshape it to have 4 rows and 2 columns, right? Easy, sweet, very efficient. Essentially, it doesn't really do, probably, if you would use something which comes with Python, probably there would be lots of kind of like big wheels, kind of cogs moving under the hood, and lots of kind of a noise, and eventually you'll get something. In this case, probably there would be just some markers placed strategically at those points, and the system would just come back with that matrix already pre-built. Okay, it's a synchronous call, and very efficient. Okay, so that's just to give you a sense of what you can do with NumPy. Believe it or not, NumPy, more specifically, it's scipy, because that was a major influence, because scipy was kind of trying, eventually NumPy was kind of a spun off. It was sort of a side artifact of scipy, but scipy really influenced the design of NumPy. So KNN, those people who have been using machine learning You know that k-nearest neighbors algorithm is just a way to identify, classify your object, your observation, or your example. So that's the standard practice, and there are algorithms in scikit-learn, but you can implement it just using NumPy. Very easy, very efficient. Essentially, the KNN uses that Euclidean distance. This is that's a formula which Pythagorean formula which finds the distance between points P and Q. So you just describe points which kind of maybe some observations of spam email, and we would like to classify that a Q point which represents a new not seen before email. As you see, just one line of code. We use linear algebra, we do that norm. It's just a way to apply that Euclidean distance metric. We find the difference, we do it by columns, and that's it. Voila, as they say. You will essentially just implement this formula, and that's what underpins KNN algorithm. Unfortunately, K is just one. K is supposed to be a number of things, like 3, maybe 5. There are some variants of that. Okay. That's a fantastic thing, meaning that you can start very simple, it's very efficient, very fast, because essentially you are not working in Python, you're working at C level, because that invocation would be done against the underlying very efficient ND array, the multidimensional NumPy array. Okay, SciPy was actually that umbrella project for NumPy, but it has many more. It's based on NumPy for all the kind of a high octane computing needs, but it also introduces lots of things for statistics, optimization, fast Fourier transformation. There is many more. You can visit that website to do a review. Pandas also helps your data science projects in creating very efficient, very well thought out data frame object, which is essentially, it's sort of a tabular data set container, similar to a relational database, table, or Excel spreadsheet. You've got rows, you've got columns, and you have ways to slice it horizontally, vertically by rows, by indices, or by columns. You can add columns, delete columns, drop columns. So again, as I said earlier, R was the major influence. Data frames have interfaces with sources on the internet. Supports HTTP, HTTPS. You can also read data from a variety of formats. The common way is to consume character-separated values. So that's JSON and what's not. Okay, Pandas already anticipates, the designers anticipated the use cases which would data scientists would have, like repairing data. For example, you have missing data, right? It might happen that something went wrong during data acquisition, maybe a sensor like failed, or your partner probably was down at the point when you were collecting data, and you will have lots of not a number thing. It's kind of a nulls. How you would treat it? The most, I guess, straightforward way is to drop the data, which essentially probably would have some sort of a threshold for that decision to be made. Like 70% of data is missing, so there is no really point. But if you have maybe 5% or less of data missing, then what you need is probably to plug in some sort of a kind of a data points that would make sense in the context of your processing task. But also you would have probably some traditional use cases for data grouping, aggregation by columns. So whatever you do with SQL, for example, grouping, applying where clause, selecting, doing that projection, so which columns you would like to be returned to you. right? Pivoting, like Excel pivots, joining, inner joins, and similar operations are supported. And those are very efficient because they essentially operate on using very efficient data structures. So here's an example of how you would plug in. So I'm just giving you an indication what you would need to do when your data has arrived. You acquired the data before you can say, yes, we own the data, you need to do something with data. Right, so Python supports the whole full cycle, end-to-end, end to the beginning. Kind of you got the data, come in to your system, and then you make it ready downstream for your model building. For example, we create a data frame. Data might come from the internet, from your local file. You can read table, you can read CSV file. And the strategy for plugging in missing data, some values, concrete values for that missing values, not a number, to use any of those strategies or methods, right? As you see, there are lots of those. Probably that guy who was doing it probably got carried away. Probably most popular would be nearest, zero, or linear, something like that. But you can explore those. Probably would have a very good kind of a corner use case. Splines, very nice. But again, if you have lots of kind of missing data, you would be better off to just suppress that data set altogether, throw it away. You can do in place or you can do copy. So in place, maybe not a good idea, but if you are concerned about your memory, then probably in place would be a good idea rather than creating, copying it over to another data frame. Scikit-learn. So that's where I guess fun begins. We've got a scikit-learn package, which essentially deals with all the most common machine learning, data mining, data analysis problems. So it's built on NumPy, SciPy, Matplotlib. Essentially, just builds on it stands on the shoulders of giants, and it does a very good job of creating good implementations of well-established algorithms in a number of fields. It's not only just regression that you would expect, but it also lots of those things. And there are lots of, I guess, opportunities for you to optimize things. It's not just one size fits all. We've got one algorithm for this, one algorithm for that, just that one size. You've got lots of things to play around with. Currently, they don't support graphical processing unit for acceleration. If you really need much faster processing, you would probably need to consider, I don't know, maybe Google TensorFlow. They support pandas, they support, and the API for algorithms is modeled after scikit-learn with predict fit type of methods. So you would be at home to go there and have maybe several times better performance, maybe 10, 100 times. What's good about scikit-learn is that essentially they created uniform API for training your data, doing prediction, transforming your data. Scikit-learn refers to those models as estimators. So estimator is used interchangeably with model or predictor. Terminology is really floating around. It's just probably it's not going to settle. People come from different backgrounds and they have their own view of treating data. So they call data as records, as observations, as examples, and so be prepared. That's the good thing. It's something that I really like about the ways they do it. It's just create uniform API. If you have worked with R, maybe with other systems, you would probably find that what's missing is it's kind of a very opinionated view of what it should be called. And you kind of have to struggle and to see how you would stitch together. I train the data, then how I do prediction, how I do transformation. And in this case, it's very much unified. And that's a very good factor in aiding in your development efforts. Algorithms expose like score method so that you can get an instant feedback on how well your algorithm performed on training data or on testing data, right? And you would kind of see what would be the good balance. It's very important to have this feedback, instant feedback, to appreciate that effort of your data model. Testing and training data splits are very important, very, I would say, indispensable. And in many cases, you can, of course, implement it in your own way, do reshuffling of records. So the idea is that you cannot really use the same data that you use for training and then test on the same data, because your model would be aware of the training model. It's kind of it learns the tricks. Imagine you are as a student in a class, and the teacher, instructor, professor essentially teach you all those examples in the classroom, and then you go on test, and the test essentially covers all those topics using the same examples. So essentially the scoring would be very high, as long as you've got good memory and you have all those kind of techy devices to kind of help you remember what was taught, right? Because you need to apply your knowledge to something that your system has not seen yet. And the common practice is just to split your data that you received into that two parts. About 70% goes into training your data, and about the balance 30% goes for testing. There are some kind of other splits. You have validation of your model. Another maybe 10% is allocated there. Then when you do validation, you apply testing. But all those things, they just come naturally when you start playing around. But the idea is to split the data. Probably you remember that kind of pipeline, data analytics pipeline, there was that split of your data. And Python gives you a specific function for this. So you don't need to really go about thinking how to best select data for testing and what to retain for validation and training. There is also a number of algorithms how you can best do it. Python gives you all that, like train, test, split function. You just specify the percentage of how you would like to break your data, what would be that threshold, and the system would perform that shuffling of the indices in your data sets, and it would select, it would also need to take into account the labels, the classes, because we've got, in the training data, we've got some predictors already, some predicted values, labels, numeric value or maybe a categorical value, which is kind of a label or class, essentially something that we want to use to train your data, so that your predictor, your variables, your inputs would help you to build a model which would predict those outputs or resulting values, usually expressed as y. Lots of things would need to happen so that it will be balanced, it would be random, and it would be even. And of course, you can come up with your own thing, but Python already gives you that. It's part of scikit-learn. There is also a class, shuffle split, where you can use it directly with some additional parameters. K-means example. So I guess that's would be the last, I guess, which essentially the final phase in your data science project, where you essentially can start trying out a model. And in this case, we are doing probably processing of unlabeled data, where we just use k-means. I'm not going to go into much detail. Essentially, it's a way to create some sort of a centroids, points of gravity, where your data would gravitate towards, and you can say that's the cluster of my data set, right? The only inputs that you have in the algorithm is the number of clusters, and usually you can play around with this. And in most cases, if you work with subject matter experts, they would probably give you a very good hint as to how many clusters you would expect. They would say there should be 2. That's just kind of a binary thing. We know we have this gut feeling, and or there might be 5 or something like that. You can play around. You can plug in 6. Nothing's really going to happen. But then you would run it by those subject matter experts, and they would tell you it looks like it's not really there. It's overfitting. It's probably not doing a very good job. The decision boundaries are too ragged. System just not doing a good job. So that's pretty much the algorithm. One line that came in, I highlighted it in red, shows you that you just get that k-means cluster from scikit-learn clustering sub-package. Random state is important to have the same data reproduced, because k-means would work by randomly placing those 3 cluster centroids, the initial position arbitrarily, and if you want to reproduce it, just do yourself a favor. It's a common parameter, random state, which I guess used in lots of algorithms, implementations. If you want to come back to that result and show it to someone, make sure you do this, because otherwise, if you don't do it, your results might be quite apart from what you got in your experiments and those results that you are showing to someone. So fit, as I said, that is estimator, and fit is the way to train the data. You're training your machine learning model on that data frame. It's pandas data frame, which we have just acquired. Probably before that, we do some processing, repairing your data, maybe performing that feature selection, feature engineering task. And then we've got ourselves k-means model. And immediately we can do dump of those centers. We've got 3 centers. We've got 3 in our data frame. Most likely we've got just 2 predictors, 2 variables. So it's kind of x1, x2. Right, and we've got ourselves very nicely arranged centroids. We've got 5, 10, and 2. Right, it's kind of a symmetric processing, and that's it. By the way, what's interesting here, you can get this k-means model and serialize it through the pickle serialization used in Python, and put it on ice somewhere. You can retrieve it, you can serialize it, send it to, I don't know, your colleagues working in an offshore team, and you can come back to it. You can create some sort of, I would say, maybe a snapshot of your algorithms, your progress. You can go back. You can check in your source control system. And then k-means can be used to predict. You would use those unseen data. Definitely it shouldn't come from the original data, because it will create skewed results. And the system would tell you the indices. So that would be, there would be 0. If we just use 1 point, 0 would correspond to that first centroid. 2 would be that that line. So that's it. You essentially you were able to train the model. It's called fit. A system immediately creates something that you can serialize and you can use it, right? Using this predicting. You can do the score. System would give you some estimates as to how well it arranged. And when you are playing with those number of clusters, that value, that scoring would help you a lot. Okay, so I've got a question. Why will you guys send this presentation to all attendees? Will you send? Oh, I'm pretty sure it has already been done. I'm pretty sure if you have seen that invitation, there should be an email. Okay. Anyways, let me just quickly check if I can get hold of this presentation. Okay. Any questions? You know what I'm going to do? I'm going to just upload it to the handouts section. I've got it just in front of me, so that's what I'm going to do. I'm putting it into the handouts to those people watching. If you want to get it, just download it from there. Okay, I see people are dropping off. Okay, so the question is, how can you tell what algorithm modules exist in a Python package? You can do dir. Dir and provides the name of the Python package name. It will give you methods. It will give you the location. And what you can do, probably the question is more of how can I just figure out what Python package can give me. Probably the best way would be to go to that documentation page. And but before you do this, make sure that you can do versioning. So if you provide that name of the package .2_ version $_, it'll give you the version. So you need to go to exact version of the package, because essentially all that software for NumPy, it's open software, pandas, scikit-learn, is given to you as is. People are trying to do their best on their free time to do as much as they can, but sometimes they just screw up. Certain functionality doesn't work the same way. Like between Python 2 and 3, what happened was they just changed the way they handle integer division, right? So sometimes it just might, I don't know, just play very nasty tricks, to put it nicely. Okay, so while people are thinking about questions, some of the, I guess, offerings. So we are currently finishing off the testing of this class, Python 2 days, which I would say kind of more of a crash course on machine learning and lots of things just happening. 2 days, very little, but at least we are gauging the interest, and we've got lots of requests from people coming from different backgrounds for something like that. Which Python version should we use? The predominant production deployment is version 2.7 or 6, but I would encourage you, if you start new projects, bump up to the latest 3.6 and do upgrades to all the packages, NumPy, pandas, because things are quite fluid in this area. And you'll never look back, so to speak. Python 3 plus 3.6 gives you a great deal, kind of a dictionary apprehension. Essentially, it's just a more pleasant environment in terms of printing and lots of things happening. Python 3. The latest, I would say. If you start using it from scratch, don't go back. Even though if you are required to port it back, it would be probably a good effort, but still you already have better agility, development agility. Okay, any more questions? Okay, it looks like people are more interested about Python rather than Python for machine learning, for data science. Anyways, thank you for attending. That's all I have to say. I do hope that you'll find kind of some ways to apply that knowledge in your future projects. Okay, all the best. Bye-bye.